Uh, Hello. Today I would like to give a summary or brief introduction from the introductory guidance to the quantum mechanics series. And today our topic would be what is briefly the Heisenberg uncertainty principle. So before we go to the Heisenberg definition, we would like to mention that mechanics deals with the atomic and subatomic scale. So for that, when we make a measurement of objects, so if we are looking to calculate some values of object which is found in atomic and subatomic level, there always exists amount of uncertainty for those particular measurements. And in fact, there is a limit how precisely those measurements can be made, and this is exactly known as the Heisenberg uncertainty principle. So it's how precisely we could evaluate the uncertainty for the evaluated measurement. So by the end of this lecture, we will see that Heisenberg uncertainty principle is a result of wave particle of matter that exist on atomic and subatomic level. Maybe in briefly, that electron is behaving as a wave, not a particle. So this is why we have the uncertainty of Heisenberg principle. Heisenberg principle itself has nothing to do with actual device or instrument that we are using to evaluate some of the measurement. So to fully understand what the uncertainty principle is, let's conduct the determination of the electron position using hypothetical device. It's not real device. And suppose this device is a powerful light microscope. So to know precisely where electron is located at specific time, then the microscope wavelength has to be very short or very small, as in the order of size of subatomic particle. And this is actually continuous to the previous class that we have mentioned. When we are getting smaller wavelength, maybe we can get higher energy and maybe brighter for the wavelength. Okay, the result of the wavelength of light by those hypothetical measurements will increase the momentum and energy carried by the photon of light. So if the wavelength is short or smaller wavelength, the higher energy will be carried and the higher momentum will be carried for the photon of those generated lights. We have this common formula, which is momentum of that photon equal the Planck constant divided by lambda. So if the wavelength, which is lambda, decreased, then we will expect that increment for the momentum will be carried with that photon. So this is, we are conducting the experiment. Suppose this is the generated light from our microscope, and this is the scope of the microscope. So this is the electron that we are looking to evaluate its position. So how exactly could we conduct the experiment? So how exactly could we conduct the experiment of determining the electron position? The microscope uses a light of a specific wavelength. Then to see the electron, this light has to physically interact with the photon. So we have to achieve kind of interaction between electron and the photon path, and this is the path of the light. Then, since the photon will carry some energy and momentum, it will be given to this electron, and this electron will be energized and get some energy and momentum that leads to generate velocity for that electron, which will be reflected to some specific direction. And the electron reflects and reach the observer's eye. That's because maybe this is I'm just repeating what I have just mentioned. So it's because during the collision the photon transfer amount of momentum and energy to that electron, which make the electron to move with some velocity in the same way once we have a shorter wavelength of photon, the higher momentum of photon and the higher momentum of electron will get after collision as well. So if energy increase, the amount of energy will be transferred to the electron increase. So the higher velocity will the electron has. Note, we can know the position of electron at that instant of collision time, but we cannot know the future position will reach, as we don't know its momentum after that. So instantly maybe we can be able to know the position, but we cannot know the position and the momentum of that electron particle. So to know the electron position, we need to apply very short wavelength. So this is just a brief summary of the previous mentioned thing. Very short wavelength of photon light, knowing its momentum and energy, which leads the electron to move with very high velocity, which will change the electron position. The position may be known at that specific position only. The uncertainty is knowing the position and the momentum at that same time is the basis of the Heisenberg uncertainty procedure. So to describe these last two lines, maybe it's mathematically expressed as delta x, which is the change in the position, and delta p of x, this is the change in the momentum of that electron, has to be larger or equal than h bar. H bar, which is the Planck constant divided by 2 pi, and this is the value of it. It is described as the constant value. So if we are changing of the electron position, and the momentum will be changed. So if this is increased, this has to be decreased. If this is the momentum increase, this value has to be decreased because it's constant value. So this equation actually tells us that the more precisely we know the position of object, the smaller delta x has to be, because it's constant value. The less precisely we know the momentum, the greater delta b, which is the momentum we have to be. So, or it has to be. That is impossible to measure the position delta x and the momentum delta b of an object with the precision at the same time. This is, of course, doesn't mean that we can't make precise individual measurement. We can, for example, determine the precise position of an object at some instant in time, but then the momentum would be completely unknown. This means we would have no way of knowing the future position of that object. Finally, the wave particle duality. I mean, why I mentioned here, just to tell finally, the uncertainty principle is an inherent property of wave and forces that matter can act as waves as well as particles. That is the reason an electron doesn't have a precise location as particle. That is the reason an electron doesn't have a precise location and momentum at any movement in time. That is because it is not actually a particle. So the uncertainty principle has nothing to do with the precision of the measuring instrument. And today's class is completed. Thank you.